Anyway, Ian did his PhD with Gordon Rule at Carnegie Mellon and joined us recently. He's actually only been here 6 months, and 3 months in, COVID sent us all home. So he was learning quickly from Frank about setting up experiments and analyzing data, doing a great job. And what he's going to do today is go through just kind of the general idea of setting up and showing you where some of the tools are at nmrbox. I will let Ian take it from there. He's going to actually use nmrbox and show you some spectrometer stuff as well. And at the end of this, we'll have a discussion period again, and then we can just talk some general terms for any questions you have at that time. Okay? Ian, it's all yours.
Great, thanks. So this will be split into 2 parts. The first part I'll be going over setting up the experiment on a spectrometer. And then in the second part, we'll be looking at some real data on this E2 protein that we've been talking about, and looking at kind of what the workflow is going from a spectrum like you see here to a bunch of curves to populations, exchange rates, and delta omegas. So instead of sitting here at the spectrometer and kind of tuning it and calibrating pulses with everybody, we're going to assume that you've been able to run an HMQC experiment. You have your pulse widths, everything is shimmed and tuned, and you're good to go. So I'll show you kind of how to set up the 4 different experiments for the geohard, and we'll start just by copying this HMQC and changing the pulse program and putting in all the parameters. So if this is all too fast for anybody, if kind of the load times are taking a second before you can see some of the text, just raise your hand and I'll try to slow down, because there's a few parameters that we'll have to change, and it's a little bit important that you can see the text. So this is the HMQC that you've run. You have all your parameters fixed for that. So we'll go and start a new experiment. So just click this. And we want to use all the current parameters because the number of scans and the sweep width and everything will be the same for the geohard. So what we'll do first is set up the R1 row experiment, and then using that kind of just copy the parameters to the subsequent experiments to make it a little bit easier. So we'll use the current parameter set, and everything looks good there. So now we will make sure we're working on the right one and go to the acquisition parameters here, so this tab. The first thing we want to do is change the pulse program so that we're running the right experiment. So we're just going to click on this ... here. We have a whole bunch of things installed. We'll also assume that you'll be able to install a pulse program, or someone will have installed it for you. And we provide the pulse programs, Frank's pulse programs. So I'll just search for SQ, which I know is part of the name. And what we'll set up first is this R1 row experiment. So we'll set that. Yes, we would like to set that. And then after that, close this window. So this is actually a pseudo 3D experiment, and the HMQC that we ran is a 2D experiment. So we'll have to change the dimensionality. And to do that, we'll click on this button here, which if you see down in the corner here, it will describe what it's doing. So we're going to change the acquisition dimension. So we're going to change it from 2D to 3D. Hit OK. So now we have our third dimension, and what we'll set it to is the QF setting. And then the number of points will be equal to the number of things in your VC list, which we'll get down to eventually. I'll set this to 4 because we'll be collecting 4 different time points for this experiment. And then we can do get prosol, So I'll be typing this down in the command line. Sorry if you weren't following along there. And I have the pulse lengths written down. So I will just do that and then hit enter. And then all of that is set up. So I said that this will be equal to the number of items in the variable counter list. So I'll have to set the list as well. So click on the lists tab here on the left-hand side and see there's a whole bunch of different options. And we want to select the VC list. And you can write a new one for this if you want to, or you can use an already available one. They're not terribly complicated, so I'll show you what this one looks like. So now the parameter is changed, and I'll open it in the editor, and we can see that there's 4 items. So we needed to set that value in the pseudo dimension to 4. And the maximum value is 8. And we'll write that down because we will need that in a few minutes here for another parameter. Okay, so now that that's all finished, we're going to have to change windows again and set up the rest of the experiment. So click on this pulse icon here. It's the second icon on this top row. And this will show a couple of different parameters. And it will complain because we don't have the right gradient names in. This is fine. We just have to set that parameter when we get to it. Just click through. Okay, so now that it's done complaining, we'll kind of set the other general parameters. So the number of blocks is also going to be equal to the number of items in your VC list, so 4. The number of scans, so, okay, it's going to complain every time I put in a parameter. The number of scans, so we're going to make a few suggestions here. Obviously, you can, your mileage may vary, but compared to a regular HMQC, what we'll do is just double the number of scans. And we'll change that to 8. Let's see. Okay, so that's all done there. And the next thing we'll do is fix the gradients so it stops complaining. So we'll click here on the left-hand side to the gradient channel and get some complaints. So I'm gonna fill in quite a few things here, so I might be a little bit quiet. What's nice is that Frank was very kind and made comments on all of these, so I know exactly what parameters to put into each of these things. So I'm just gonna go ahead and start entering in the different gradient names and then the different values. So if anyone wants to fill the time, they can feel free to do that.
Ian, I'm going to make a comment while you fill those in. So someone may wonder why we don't just distribute a parameter set so that you could load all of this. Our recommendation is that you do this at least once and you go through and see that it's set up. Part of this is because if we create it at one frequency and you're going to run it at another and you have to adjust these, once you've set it up on one spectrometer, you can clearly write your parameter set and save it, and then you have fewer steps going through. But this makes certain you go through and you check and you see what's happening and you know what's going on. It's not that much, and as Ian will show you, he's just going to step through this and enter those values that are suggested on the right side and get these things set up. So then once you have this, you could write the parameter set on that spectrometer with that probe, et cetera, and be very close, such that when you go to run it, repeat it on another sample or another system or something, it'll be pretty much set up.
Hey, Ian, while you're typing, is it possible for me to ask a quick question?
Sure.
So if of all the gradients, when it's SMS Q10, why only one of them is sine.100? Is it very critically different? I thought we pretty much good old days sine 100 and SMS Q10 is the nice sweet compromise between a square gradient without the edge effect. So is it critical that it should be sine 100 for GPNAM4? Probably you will explain that with the pulse program, but just I'm jumping the gun.
I'll defer that question to somebody else.
Okay, no problem.
If Frank.
I think you are correct and not necessary. You can change the gradient because this one is just, remove the artifact due to the imperfect pi poles. So
Okay.
you can use other gradient as the reason why I said that is just, give a reference. If you don't like this gradient shape, you can change another one too.
Okay.
Yeah.
Thank you.
Okay. So now that that part's over with, and we kind of just filled in what was on the side, there's a few other parameters that are misset here, which is why it's complaining. So we need to alter these. So this is set to 1 millisecond, which it is. This needs to be set to 500 microseconds, and this should be set to 200, not to 2000. Okay. So now that we're finished with the gradients, we'll go up to the proton channel. So we'll click channel F1 here. So what we have to do here is, okay, so it did mess up a little bit, is we have to put in the flip back pulse, the water flip back pulse. So there's a few things that we'll have to change. So the first is the actual shape pulse. So we just went into the wrong directory here. So this is the user directory, and we need it from the regular library. No, that's annoying. Sync, that's right. Okay. So that was just misset from copying the experiment over. And then we'll have to change a few other settings here. So P11 will change to 1 millisecond as it's suggested here. And then we need to calculate the power of the pulse. So we'll do in the command line, prosol. And here we have the wrong value in here. So our pulse width is 8.6. So just change it to 8.6. Set. We'll calculate by clicking on the calculator button. And then we want to go to the shaped pulses tab. And we'll look for our water flip back pulse. So at 1 millisecond, we need a power of 26.3. So we'll close this, select, okay, so 23.6.
Hey, Ian.
Sure.
So normally the get prosol, when you enter the pulse, the nucleus, pulse width, and power level, it's supposed to calculate all this, right? According to that basic value. So
Right.
why you have to change it in the prosol?
That's good. I'm not sure why it didn't change because it did run.
I mean, unless the pulse, the parameter, the relation, so the mapping is not standard or obvious. Probably that's the only place where I see it doesn't calculate on the fly.
Yeah.
So okay, this could be because it's your own pulse program, right? So is that the reason?
It could be.
Rajan, there are some issues with relations files, and we have toyed with going in and building all of this stuff in.
Oh, okay.
That's a little risky because Brooker tends to change things.
Yes, you bet.
So I have some relations files that I have written, and my pulse sequences use them.
Okay.
But
yeah.
I'm hesitant to change something that gets used generally.
Okay. Yeah.
Okay.
Yeah.
So this is a few more steps. You're right, but a little bit of care is judicious here.
Okay. Yeah. Thank you. Yeah.
Okay, and then this is the last parameter here that we have to change. So now the proton channel is done, and we'll move on to the carbon channel, which is just slightly down here. So here there's a handful of different things that we have to change. This is kind of the most important part because we'll be dealing with all the power levels here could potentially do some bad things. So as long as you're kind of careful here, there's only a few things to change, and there's only like a little bit of strangeness. So it shouldn't be too bad. So what we'll do is we'll note down our carbon pulse length, which I have 7. Yeah. And then we'll do ED-prosol again. Okay, so again, it's not changed. And this is going to be in the decouple column. So we'll do this a second time, unfortunately. And here we're going to be, so we don't have something in the kind of relations table here. So we have to make a new section. Again, once you run this experiment, you can save a parameters file, and then you have a starting point for your next one. So this is kind of a once and done sort of thing. And then you just want to make sure to check the next time you do it that everything is kind of, the power levels are all where they should be. So just name this anything. And this is going to be for the adiabatic pulses. So, and then the pulse, so the flip angle will be 360. And the pulse width is going to be 1/7 kilohertz. I've already done this math and written it down. And Frank has, oh no, wrong section there. Frank has done this enough times that he just memorized it. So the pulse width will be 142 microseconds. So the power level that we need to use is negative 12.26 dB. So, none. Okay. And this is going to go in here. In the power level, or shape pulse power 24. So after that, so we have that important part down. Now we want to select the shaped pulse for this particular experiment. So for the R1 row and R2 row experiments.
Ian, do return on that. There you go.
So for the R1 row and R2 row experiments, you'll need to just copy this a number of times equal to the number of different shape pulses that you want to do. So this particular experiment will be the R1 row with the HS1 pulse. To do the HS2, you would copy this again and select the HS2 pulse, etc., until you're done with all 4 of them. So I'll set up for HS1. And I need to be in the user directory here because this is a custom shapefile. HS1. And we'll select the _FC. We won't worry about that other one. Okay. And it moved on me. Okay. So then the next part of this is changing this constant. So this is the scaling factor. Here in the comments, we have different values for this. So depending on which shape pulse you're doing, this is another parameter that you'll have to change when you copy the experiment over. So for HS1, we'll be doing 0.295. So I'll fill that in here. This is another thing that you'll have to check every time you choose a new shaped pulse for a different experiment. And then like I said a long time ago at this point, for L5, we need to change this to the maximum value that's in the counter list. So I had this written down as 8, the last number in the VC list. So we'll change that to 8. And then this is for the temperature compensation. So kind of as high as we'll go is 10 for this value. But usually, you know, I think for the R1 row, 8 is as high as I've done. And it's kind of just whatever is in your VC list. I wouldn't go much higher than 10. Other than that, this is, I think this is all done. Just reading my notes here. And what we'll have to do to run the full data set, so that to get the rate at the different shape pulses, is just copy this 3 more times and select the different shape pulses here, and then edit the scaling factor. So instead of doing that, I'll show you kind of the different, setting up the other experiments. So the R2 row, the R1 and the R2. So let's make another experiment here. And while I'm doing this, if anyone has anything to add, Frank or Andy.
Hey, yeah, I had a question.
Sure.
So the hyperbolic secant pulse, did you use STDISP to generate that, or do you have any of you used the new feature where the shape pulse can be done inline in the pulse program? And were you successful? That's one thing. With Topspin 3.6.2, the pulse program, there is this shape pulse can be generated in line in the pulse program itself. I haven't really played much with it, but I just read through. But any of you have used it? That's one question. Another is this the hyperbolic secant. Did you use if not, did you use the STDISP, the shape tool? Is that what you use to generate those pulses? Thank you.
Okay, let me answer this question. It's important you have the shape file. I actually generate the shape file by myself. Okay, I didn't use any tool.
Oh,
and
I see.
I have the shape file and use that to generate the library. So the library and the shape file need to be coupled together. So they cannot get separated. You cannot use the arbitrary shape file, arbitrary, then run the experiment, then analyze it with my library. That won't work. So you need to use my shape file, because that one was used to generate the library.
Okay,
so
okay, yeah.
Make sure everything is consistent.
Okay, okay. So it's not just like, yeah, sorry.
So if you remember the track analogy, the path that those guys go on is dependent on the shape, and the analysis is dependent on that path.
Correct.
So they have to be linked. Now, you could use DSP to look at what its frequency dependent is, but that may just be for your education. They're going to look like hyperbolic secants with some variation.
Okay, I see.
The other thing you're talking about is WaveMaker, which is sort of the, if we don't have any vendors on, well, maybe we do. Anyway, that's written by Eric Skupchi, okay?
Yeah.
And so it does have flexibility, but again, and so you can do that, and there's some really cool things you can do with putting it right in the pulse sequence. But the problem with that is that it has to match the library. So that's really the key component that Frank explained.
Oh, thank you so much for that's very important to understand. Yeah, thank you.
Okay, thank you for the questions. So moving on, after we've got the R1 row set up, the R2 row is fairly simple. We need to change the pulse sequence. But pretty much everything else is good to go. So we'll set the pulse program. And just a note, because I don't think I touched on it before, these parameters here, so the spectral width, you'll have these set from your HMQC. And these first 2 channels are going to be the HMQC. And then this channel, it doesn't really matter what's in here because this is a pseudo dimension. So these won't really affect any of the spectra. So one thing that you could change with the R2 row is if you wanted to use a different UC list, just scroll down and change that. For this, I'll just keep the same one of 0, 2, 4, 8. If you've run this experiment before and you know that you might need different values in there, you can always change it for the 2 different experiments. As long as you keep the temperature compensation value the same for both. So that's it for the R2 row. That was simple because we did everything the first time in the R1 row experiment, and they just needed to copy it over. So then we can move on to the R1 and R2 experiments. So I'll do the R2 experiment first. So again, we'll make another, one other note is just like the R1 row, for the R2 row, you'll need to make 3 more experiments, each with a different shaped pulse, and then changing the value of the scaling factor and changing the name of the shaped pulse for the adiabatic pulse. So let's do R2. 4. Go to our parameters, select the pulse program. That's it. So here there's a few things that we'll have to change. One is we'll have to change this value as well as the number of blocks because we'll do a larger list than what we were doing for the R1 and R2 row experiments. So we'll scroll all the way down to the list section and choose a different list. Let's do R2 here. And I'll show you the list. So here there's 8 values. Each of these is, that's right. So then we'll have to change this dimension to 8 instead. And then when we swap over to this pulse tab, we'll also have to change the NBL, or the number of blocks, to 8. Just so that the data is collected okay. So then there's one other value that we have to change, and that is in the carbon channel, so F2, as we have to change the where is that? Oh, sorry, that's up at the top. So okay, thank you. So the D5 here, we'll just have to set it to 0.66 milliseconds. So you can see that this is in terms of seconds. So we're going to have to put a couple zeros in there. So that's changed. And then the last one is in the carbon channel. And so this is the 180-degree pulse, because in this sequence we have 180-degree pulses similar to a CPMG experiment. So we'll just need to put the values for the pulse widths and the powers in for those. So if we're using a full power pulse, which I'll just use a full power pulse here, the length of this will be the same as the length of P4. So that'll just be 23.4. And then the power will be, okay. So the power will be the same as well. So it will be, this is a, yeah, and Frank, what do you put in here?
21.9.
The 21.9.
Minus
okay,
21.9.
I know that you could also do half power pulses here. So that's what I was just getting stuck on before. So if you use a half power pulse, you have to just change the length of the pulse length. So you would just use half the value here and change this to times root 2 but we're just using a full power pulse instead of getting confusing. So that's the R2 experiment. So the last one will be the R1 experiment. So for these, unlike the R1 row and R2 row, you only need to set up one because you're just getting the R1 value or the R2 value. You're not getting it with the different adiabatic pulses. So we don't need to copy this 3 times and change anything. So we'll set up the last experiment here. We'll name it R1. And this is a fairly simple experiment. So we'll change our pulse sequence. And then instead of using a VC list, this uses a VD list, so it delays. So we'll get rid of this value here. And we'll just change the VD list. We already have one. Again, you can make another one, that's fine. And then this is just the values here. So this is a 9. For some reason, this is a 9 item list. So again, we'd have to change the size here. And then if we go into this section, we'd have to change the NBL to 9 as well. And that's it for the R1. So that's all of the experiments. So all of these are coded so that you can check the time. So if we just display, for instance, the R1 row, and you can click on the clock or run EXPT, it can do a time calculation. So that will take, with the current setup, it will do it in 4 hours. So times 4, that's about 16 hours. So a few days to collect all of this data. And then after that, we'll get into the next part of the talk where we're going to analyze the data. I saw my Zoom thing pop up there. The chat. Okay, so Frank's answering questions in the chat. Okay. So does anyone have any questions before we kind of move on to doing the data analysis rather than just the acquisitions?
While you switch, Ian, I'm going to make one comment because it affects setting up the experiments. We talked in the 2 presentations about, you know, an R1 row normally puts great stress on your probe. In the C13 experiments that Ian just set up, the pulse shapes are designed for a peak RF power. This is the peak power, not the average power, of a 7 kilohertz field. Those were some of the numbers he used. So that corresponded to an equivalent 90-degree pulse of 35.7 microseconds, which is, you know, like 3 times as long as the typical carbon high power 90. Okay, so it's not stressing the probe, and that's the peak power. Even though the pulses are on for, you know, a few milliseconds, the peak power is for a short time, and it's down dramatically from what the high power is. So the probes are safe in that. In equivalent case on the N15 experiment, the shapes are designed for a 3.5 kilohertz RF field. That's an equivalent 90-degree pulse of about 71.4 microseconds. Okay, so again, that's considerably lower than the full power pulse that you would use in a CPMG, where the 90 might be, well, depending on your probe, 30 microseconds up to 45 microseconds. So these experiments are pretty probe tolerant is basically, I think, all we can say. And they are set up, well, the N15 will run even up to 800 or 850 megahertz, and the methyl will run up to 1.2 gigahertz based on the shapes, and we may continue to evolve that a little bit. Okay.
Okay, thanks, Andy. All right, so now we've we'll fast forward a little bit and pretend a few days have passed and we've collected all of our data. And now we have it conveniently placed on nmrbox. So if you want to follow along with this, this is available in the, I'm going to be using the command line. So if this text is too small, just let me know. So this is available in the public summer workshop 2020, in the byrd folder, and then in the practical folder. So I have this copied to my home directory. I would suggest you do the same, or else everyone's going to get what you're doing in the public folder. So
I think just to point out, I think it should have been done automatically for all the registered participants.
oh, great. I don't know, I was changing stuff today, so let's see. Okay, so this has a few of the processing scripts already in here. I just copied them over, and it already has process spectra, so we're not gonna go through that whole thing. We'll assume that you have process spectra already. So I just have NMR draw open here. This comes with pipe, so we don't need any other programs here. I have a script after this, which will do all of the exponential fitting to the rates. So this is doable just with pipe. So this is what our spectrum looks like. I'm going to be focusing on the isoleucines just to reduce the number of data points here. So if I zoom in, we can see that this is a nice spectrum with very pretty peaks. There's only a little bit of overlap between these two here. And what we'll do is just process this for all of the individual 2Ds in the list. So to do that, we process the whole data file. So the data file we get from Topspin as a two-dimensional experiment. And the way that we can do that is just by looking at the number of, just multiplying the number of points in the pseudo dimension by the number of points in the carbon dimension. So if you look at the AccuS files, or you can run the Bruker command in NMR pipe to process these. So if we look for a time domain Q2S, is 120 points in the carbon dimension. And then if we run it on it for the pseudo dimension, there's 4 points. So 4 times 128 is 512, which is what's in our fid.com. So this is using pipe to process it. And all the other parameters are just pulled from the acquisition parameters. So once we run this, we get a large two-dimensional file, which we need to split into the separate 2Ds. So this is just a script. I got this from Frank that just goes through and splits each individual one, because this is an interleaved experiment. It splits each individual one into a separate 2D. It does this pretty basically. So for this, there's 4 different things, because if we look at our VC list, there's only 4 items in here. Sorry, it's kind of overlapping with that. There's only 4 items in here, so there only needs to be 4 here. For the R1 and the R2, there would be instead 8 or 9, depending on what your VC list had in it. And then it just processes each one exactly the same. So what you get is 4 spectra like this, and then for each different item in the VC list, for each different counter. So once we have this, I was just doing this in pipe, so in NMR draw. So I just picked the peaks. So this is a little bit messy. The fonts are kind of funny, but we just pick the peaks, and then I have this saved to a peak list. So it's the test.tab file in this directory. So that has a bunch of information that we don't need. All we need are the peak heights from these. So there's just a short little script in this directory that we can run that will extract all of the heights and give us kind of a normalized value for each. So the first will be 1.0, and then after that it will just decrease. So I'll show you how to do that. I have this in the public folder, but that's fine, I can run it here. So because it's NMR pipe, we need to run this in C shell. So to do that, I'm just running CSH-C because I don't have the setting there. So if we run norm.com, it'll run pretty quickly. And then if we take a look at the output file, which is norm.txt, a bunch of useless information, and then this is the stuff extracted from the peak table. So it will give you the atom ID, so what you named it, what you called the peak, the proton shift, the carbon shift, and then this is the height for the first one, normalized to 1, for the second, third, and fourth. So this will serve as the input for the exponential fitting, which I'll do the next window here. So any questions about processing? It's kind of like people do it different ways. So this is just how I was doing it. If not, I'll move on to fitting some exponentials. So
Hey, Ian, sorry to interrupt. One question, quick question.
sure, no problem.
Andy also mentioned this. So this is the NMR pipe route. Is this amenable to sort of import into the FX process, which Bruce Johnson talked about a couple of weeks ago? So NMR FX, and I think that also has tools to fit R1 row and so on, right?
This
Sure.
is Bruce, I'm processing it right now as we speak in NMRFX.
Oh,
Oh, okay.
Oh, Bruce.
There he is.
I think what you want, Rajan, and Bruce is going to have them done here by the time we're done, is basically you just want to fit these and get the exponentials because it's those rates
Yes.
that are going to go into the fit to extract the kinetic parameter.
okay.
Yes.
So yeah.
So Bruce will have a script for you here in about 30 seconds.
Yeah, we'll see.
Okay, so we'll race to get this done then. Hopefully I win. So I just wrote a script here that just reads in the individual things. So if you wanted to use this in your own work, there's only a few things that you have to change, and it's at the top of this main function. So the carrier, So the carrier frequency in hertz, this is just collected from the ACU2S file. And then just the names of the data directories that your data's in. So for R1, I have it in 200. For R2, I have it in 400, and then et cetera for these ones. So this is a list because there's the 4 different experiments where this, you only need 1. So maybe you were astute and noticed that I'm in the byrd practical 600 data file. I forgot to mention that. So if you go in here, if we go into 100, which is where I was on the previous screen, that's what has the norm.com, the processing file, and the actual data, so the spectra. If we kind of go back to the top level, not the top level directory, but the 600 data directory, this is where this fit exp.py file is. So I have a folder here for called prefit. So I did this earlier to make sure if there are any technical difficulties, we can still look at the data when we're done. So this runs pretty quickly. Essentially all it's doing, so I can run it while we're talking. So this is a Python 3 thing, so you're gonna make sure you say Python 3 fit exp.py. So I'll run that, it'll give you a couple of things to say where we're at. So essentially all this is doing is reading those normalized files. So what we got from that norm.com script, so the 1, 0.5, 0.3, et cetera, and fitting it to an exponential curve, right? So it's already done. And then there's just a whole bunch of silly data handling things. And what it will output is both a plot of the curve and the formatted data that can go into the geohard fitting program, which I'll show in a second here. So once we're done with this, if we open up the fits directory, we'll have a whole bunch of exponential fits. The names of the files are kind of what they are. So this is the isoleucine 57, like in the middle of one here. Let's go to the first one. Okay, this is the isoleucine 57 R1. You can see there's a nice exponential here. The R1 row with HS1, the R1 row with HS2. And it's kind of, you can see that the rate is different if you squint, but it's kind of hard to see that. So I also have it plotted as a function of the HS1, HS2, HS4, and HS8. So this is the fitted value for the rate, the R1 rate at the different shaped pulses. So you can see we have kind of this curve going upward here. And then if we look at the R2 row, kind of have a curve like this. So we can kind of step through these. I'd recommend stepping through these to make sure you don't have any kind of anomalies like R1 rates that are just a flat line or something like that if you're running it on your own data. So here's a nice one with isoleucine 82. So here's the R1 row at the different shaped pulses. And this is the R2 row at the different shaped pulses. So this is actually what we'll be fitting, is this information here. Once we move on. So these are the inputs for the particular, or for the geohard analysis software. So I'll just open up what this looks like. So this is for a single field, the data that we went over there. There's actually two different fields here. So if we look in the field column, there's the 200 and the 150. So this is actually the data that we just fit, this whole section down here. But instead of just going through and hopping through every single thing and picking peaks and fitting curves, we'll just assume that we've gone through that kind of arduous process. The good news is that it's fairly automated, so there's not too much to do. It even reads which shaped pulse you used. So if we open up our data file, we can see there's a handful of information that the fitting software needs. So the first is just what experiment it is. So if it's the R1 row or the R2 row, then the field, the name that you chose, and then the offset from the carrier. And this is in megahertz. The R1 row, which will, of course, is output by the script in the correct units. That's not actually 0. I just tried to simplify this by getting rid of some decimal places. So these are going to be the same for both the R1 row and the R2 row rows. That's a lot of rows. So these are actually the fitted values from fitting the exponential. And the same for these 4 columns here. So this is kind of the important data. So this is the R1 row under HS1, HS2, HS4, and HS8. And then the shape pulses are slightly different for the R2 row experiment. So this is HS1 again, HS4, HS8, and then this HS4 1 millisecond pulse. So this will serve as the input for the kind of library search, and will be that kind of the actual information you get out of the library search will be your KEX and your PB and all of that. So let's move into that file. So if you're in the practical, this is actually at the top level. So we were in 600. This is the same Excel file I just had open. It's just a .txt ending. And then there was a little kind of bug, so I needed to add one of the libraries here. But on nmrbox, we already have the libraries uploaded. So the things, the grids that we'll be searching through, and we have the Python script available everywhere. So if we type in MC sampling methyl, so there's 2 different ones. One is for doing methyl, and the other is for doing amide, and they're nicely labeled. And then you need to supply the data file. So I will supply hard data. And I'm just going to output it to the terminal. If you wanted to output it to a file like fit.txt, you could do it that way. But just to kind of show you as it's happening, how long it takes for an individual fit to happen.
Expand your window a little bit first, Ian.
Okay. Do you need the, oh yeah, there's a lot of numbers.
Yeah.
It's a lot of numbers about to come at you. So I'll start running this. So there's a little bit of a lag to start, and that's just the program loading in all the libraries. So the libraries are fairly large text files, which just have the individual grid points. But once the libraries are loaded, you'll start seeing the individual fits popping up as they get done, and it'll be a lot faster than this first initial lag. Let's just see. So while we're waiting for this to finish, I will check any questions that we might have. Okay. If anyone has any questions, you can talk, and then I'll just kind of explain what's going on with this MC sampling script. All right, so there one is finished. Sorry, I keep interrupting anyone who wants to ask a question. So this is for isoleucine 41. There's a whole bunch of numbers here, which I'll show you in a second what each of those is. The first one is the, there I have it listed here. So this is isoleucine 41. This is what's shown on screen right now. If we kind of put them next to each other. So the 0.7, it's a little bit different here, but we'll explain why that could be different on individual runs. So this is the output file. It will be the delta omega in kilohertz. It's the KEX, and this is actually not a 3, it's supposed to be 2. In units of 10 squared, so this is 1700. And then the population of state A. So this is kind of the actual information you want to get out from this analysis, right? Of if you have a particular isoleucine, what are the exchange parameters? And this gives you the value and the error from the fit. So to kind of, go ahead. Sure.
So to just wrap my head around here, the software, the script automatically figures or tries whether it's a 2-site or 3-site exchange, which Frank was talking about. It
assumes it's 2-site.
It assumes it's 2-site. Okay.
Yes. So this is fitting to a 2-site exchange model. The individual libraries have to be computed for the particular exchange model. So this library uses a 2-site exchange model. So,
okay, so what's available in nmrbox? So we can say, okay, right now it's a 2-site exchange is what it will assume and then analyze the data for any of the exchange kind of data we upload.
Right.
Yeah, okay.
So just to kind of explain what's going on while this chugs along. So we're doing 100 runs for each residue. So it'll import the data, and then it will kind of start to search the sample, the parameter space in the library. And to do that, it's a Monte Carlo sampling, so it'll just choose a random location. And the goal is to kind of cover as much of that space as we can to do some type of global optimization. So each one will kind of choose a starting point, and then we do simulated annealing for 10,000 runs to try to search over the space of doing a random walk, so moving from place to place to try to cover as much as we can. And then once that part is finished, we do accelerated gradient descent to try to finish off where, we do a gradient descent to try to finish off and get to the minima in that particular spot. So in addition to outputting just this value, it will also output a file. So let me just open a new terminal tab here. This is going to be fairly large and confusing, so I'm sorry about that. So this is essentially this same information. So this is going to be the average. Each of these columns are the same. So this is for each individual run. And it's just sorted by this value here, which is a goodness of fit parameter. And this is 100 different Monte Carlo runs. And what we do is we take the top 20 of these, so that many, and average them, and then get the standard deviation from that, and that's what's reported in the end. So by doing this kind of distribution, that gives us the ability to give these statistics of what is the approximate error of the fit from doing it from loads of random points on the grid. And these are things you can change. You can do more runs, or you can do fewer. But we found kind of 100 seems to work fairly well. And it's kind of a trade-off between, do you want to be computing forever versus do you want to be, because we already computed the libraries. Do we want to be computing forever, or do we want to kind of get an approximate answer right away? And then if we find something interesting, go back and refit the data kind of with a longer or more extensive search. So yeah, just to note one more time is we don't need to compute these libraries. They're all available. So this is just reading in the library that's on nmrbox. And you don't have to do any of the hard part. So this is the extent of the data analysis or data processing. This is how long it's going to take for a particular sample, which is almost finished here in the 10 or 15 minutes that it's been running.
Ian, I have a question.
Sure.
Would it be, I noticed that your whole calculation right now is single threaded.
Sure.
Is there a way that you can multi-thread the calculation for each of your 100 or starting points, or at least multi-thread on a per residue basis, so you can be calculating each residue at the same time?
Sure. That's definitely something we'd be interested in. It's because grid search is it's like embarrassingly parallel, right? You can just do a whole bunch of different process or a bunch of different threads running it. Right now it's single threaded. And that's partially because it's just a simple implementation of it. That's partially because of Python.
Okay.
But yeah, it's definitely something interesting to think about, is how can we speed up this calculation, which is the only thing between you and analyzing your data. Does anyone have any questions? This is just going to run. Other than that, I'm pretty finished here.
So this table finishes and then you just port it to a .txt and with delimited, and then you can open it up in the Excel file.
Yeah, so yeah, I've already run this and I have it here on my computer.
And that's what you just did here, yeah.
And just kind of cleaned it up a little bit. So sorry, that should. These are parameters used in the fit. So if you're wondering what these are, just ignore them. Don't just ignore them, but don't think about them too much. These are kind of the parameters that you want. These are the exchange parameters. And then this is kind of just a measurement of how good the fit is. So once this is finished and you want to start looking at, where is their chemical exchange? Are there things that have similar populations? Are there things that have similar KEX? These are kind of the 3 columns that you're most interested in. Okay, so I see a question from Harshad. What should the minimum dispersion in R1 row and R2 row be like? So I'll try to answer this, but if Frank wants to correct me or also answer it, it's kind of complex, the dispersion curves. So
Let me answer the question for, there are two similar questions. So basically, I think the problem is, because we are doing the Monte Carlo sampling, so your energy surface is shallow, and then you will see a huge deviation, sampling deviation, and that tell you your answer is not reliable. Okay, so like so I know people like to use like a 2 per second as like the what did you call the threshold to whether you want to fit your CPNG data or not. But that's one of the reasons we know the CPNG data potentially has some potentially has more error there, because constant time and also depend on the sample. But sometimes you can see also feed your dispersion profile with like 2 per second if your intrinsic R2 rate is small. Okay, so it's all depend on the ratio between your RES turn to your intrinsic realization rate. So if you fit that, in the case like if your intrinsic R2 rate are really really large, to be honest, even 10 per second doesn't mean anything. Okay, so like if your intrinsic R2 is like 100 per second, then you have RES turns like 10 per second. To be honest, this is like, where you will start to ask yourself whether you can get an accurate dynamic parameter. So I think there's something we still need to look at the relative scale. The RES turn you measure compared to your intrinsic realization rate. And when we do the statistical analysis, actually we do the Monte Carlo sampling, which is like a random search that incorporate the statistical analysis inside. So potentially help you to test out whether the output answer is reliable or not. Of course, other people have a better idea, brilliant approach that we are welcome you to do it in a different way. Okay.
Sure, and if you're looking for data to like omit to try to speed things up, it doesn't take that long. You might as well just fit it, and you have the statistics to say, like, if your standard deviation is very large compared to the parameter, then it's probably not a great fit. So just ignore it. Okay.
I saw there's an interesting question. Yes, that's a great question regarding the slow exchange problem for the spin lock experiment. You will see that oscillation, which already proposed by Risque and other people. So in my experience, that we always see a mono explanation in the adiabatic R1 row experiment. One of the reasons is we do not, because one of the composite adiabatic pulse is 16 milliseconds. Okay, so the chance you can see the initial oscillation is really rare. So then also we find out the oscillation in my simulation rarely happen in the adiabatic R1 row experiment. Okay, so there might be another benefit. So as R2 mentioned in his question, yeah.
Hi, I have a practical suggestion, not a question. If I can do it now.
Sure.
First of all, these were all great talks. Thank you, all three speakers. It was amazing. This is just a practical minor thing about the porting pulse sequences and relation files and defining shape pulses. I know there's an elegant way of doing it regardless of Bruker conventions, because you can define relations files that are pulse sequence independent and ported together. An example of that is the IBS library, and I've sent everyone the links to the IBS webpage and to the paper that appeared last year in JBNMR about how to port this elegantly. Just a small number of Python scripts that will set up everything. And this is also field independent because they're calculated relation. So that makes it very friendly for distributed. Of course, that is not to take out any of the huge educational value of setting these things manually within the group, but when distributing the pulse sequence, it will make it clearly more popular and less intimidating.
Yeah,
Thanks, Gabriel. I didn't know about the things at IBS, so I'll go have a look. I've had a love-hate relationship with the relations files. So if they have some really nice Python scripts that fix that turn that into a love only, then that would be wonderful. Thank you very much.
It was hate for me for a decade, and I was talking to Eric Skupche and to Clemens about implementing on the fly things like Varian did, and they took that very elegantly. And IBS, it's a perfect implementation, very elegant of exactly what we wished for quite a while.
Okay, that's great, because yeah, I've had the hate relationship with relations files. And I have a number of them, and I don't think I have a favorite at all. So maybe I can be convinced. That's wonderful. Thank you.
So that raises the obvious question. So if IBS has solved the problem of moving these things between Bruker spectrometers, what about those of us who are still stuck with Agilent or Varian instruments?
I know there are
You need
translators.
to get a sailboat.
Andy, do you know of anyone doing the hard experiments?
On a Varian.
Yeah.
I don't know whether, Frank, has anyone bugged you about that?
No, original experiment was done in Varian machine,
Yeah.
but those code have a hard time to penetrate. So because I now become Booker person, so
Yeah.
I don't know how to deal with that.
Yeah, I think the short answer is no. It's not terrible, so the issues, I think, are not so much just the straight timing diagram and the pulse sequence, but the interleaving, and there's just conventions in each sort of environment.
Sure.
And Frank has got much more stamina than I do, but my stamina ran out in being able to speak both languages. And so I've probably forgotten what I knew about how to do that. But the actual timing diagram of the pulse sequence is not complex or a problem. But, Frank has written some very nice things, with temperature compensation and interleaving in the pseudo 3D, so that they're really convenient and take out any sort of systematic errors in the pulse sequence. As you can imagine, you need to do that in these things. And that's all well done. And I think doing that in the Varian system, we would have to go find a former Varian App Lab person and get them to do it.
Yeah. Well, Eric Skupche.
Eric's is probably the best. The other one I was thinking about was Ron. And I don't know where Ron is now. Anyway.
I have
Yeah.
another suggestion for a Varian Agilent guru that's expert in Bruker now. It's Marco Tonello at NMR.
Oh, Marco, yeah.
Oh, yeah. Sure.
He might do it in a weekend.
Spoken like a true refugee from NMR fam.
Yeah, I'm volunteering other experts.
A wise man. Wise man.
Are there any other questions that our august speakers today can address?
I have a quick practical question. I just want to clarify, in the sample data, there's experiments 101 to 103 and 300 to 303 and 200 and 300. We just run through what each one is.
Sure. Yeah. So you just open up the thing. So I'm sure you're just still trying to fit it. So the R1 experiments are in 200. The R2 experiments are in 400. The R1 rows are in 300 to 303. And the R2 rows are in 100 to 103.
Got it.
Yeah.
And like 100, 101, 102, 103, those are the 4 different shapes.
Yeah, so that'll be the same experiment, but just with the different shape pulse. And you can just, I think if you look in the AccuS or whatever, I think I'm just parsing the AccuS in the Python script, and I think it's under the shape pulse name. You can just grab it
Right.
To figure out which one it is.
Well, if there are no further questions, let me thank Ian, Frank, and Andy once again. And I'd like to turn it over to Andy for a last word.
I guess I should show my face here. Yeah. Okay. Thanks, Jeff. I really am very grateful to the Box team for both providing a great platform because, you know, honestly, when Frank proposed this idea and we started working on it, we kind of realized some immediate advantages that would come from this, but we couldn't imagine how we were going to make this palatable to other people and to move it around. So unfortunately, the Box project was coming along, and so it's a great example where you can take these libraries. We only have to put them in one place and put the code there, and so it can search. And we don't have to, as you can see, we don't make the smoothest tools. We make pretty neat tools, but we don't want to worry about installing or running and stuff in different places. So you can go to Box, the libraries are there, and you can do the fits and do this. And so you can experiment and play with it and try it out. And that's really all we want to try and suggest. You know, I think I said in the beginning, our motivation was we saw things that we were certain there was motions and dynamics, and it does turn out that they're fast. And so when you're in that range, all of the fantastically elegant work and incest through CPMG and R1 rows to some power levels were great, but you know, we still need that window to be a little bigger, and that was really our motivation. And I'm so grateful to Frank for all of the developments and stuff. And so we'd like to see people just try it out, give it a whirl, get in touch with Frank and Ian and I, and we can help, we'll help. So I think things are faster than we think. And unfortunately, you know, we talk about within the exchange window, we didn't, until you start doing a bunch of these and you start to wonder, you know, that when you can only pulse up to about 1500 Hertz, you realize, you know, that window isn't very big. And so you got to open that window. So that's what we hope we give you a little bit of insight as to how this may go. And there'll still be some more developments coming. And we hope to apply it to a bunch of systems. So I appreciate the opportunity, Jeff and the nmrbox guys. And I thank Ian and Frank for doing a great job to handle the hard stuff for me.